Welcome back. In today's class, we will discuss about problems on capacitors. In the last video lecture, we have seen about the developing expressions for parallel plate, spherical and cylindrical capacitors. And now we will try to solve simple problems on capacitors. I hope that by the end of this lecture, you will be able to compute capacitances of different configurations. Coming to the first problem, see. The question asked is determine the capacitance of a parallel plate capacitor composed of tin foil sheets 25 cm square faced for plates separated through a glass dielectric of 0.5 cm thick with relative permittivity of 6. See, once again, breaking down the sentences, determine the capacitance of parallel plate capacitor. So what he wants? Capacitance of parallel plate capacitor he wants, and we know the formula for this one. It is epsilon naught epsilon r a by t, right? And he's saying that composed of tin foil sheets. Okay, so sheets are tin sheets and 25 cm square faced, which means face is 25 cm. And it is a square faced sheet, so which means the surface area, or what you call it as an area, it is 25 cm whole square. So it is 0.25 meters, right? So I'll take it as 0.25 meter whole square, or I'll write it as 25 into 10 to the power of minus 4 meters square, right? And next is for plates separated through a glass dielectric medium is glass, and with a relative permittivity of 6, epsilon r is 6, and 0.5 centimeters thickness is the dielectric, which means separation between the plates, or thickness, or d, what you call it as, it is 0.5 centimeter, or it is 5 into 10 to the power of minus 2 meters. See, d is there, a is there, epsilon r is there, and epsilon naught also, you know the value, what is it? It is 8.85 to 10 to the power of minus 12. So if you substitute, you will get directly the value of capacitance of parallel plate capacitor. Yeah. See here, this is the area of plates, 25 into 25 square centimeter. Separation between the plates given, relative permittivity is also given. Now, this is the formula, and we will substitute our values. Epsilon naught value, this is epsilon naught value, this is epsilon r, 6, this is a, this is thickness, and we will get the value of capacitance. P means it is 10 to the power of minus 12. Okay, so this is the way how we calculate capacitance. Now, see the problem. Now it is a little bit bigger problem. Two parallel conducting plates 3 cm apart situated in air are connected to a source of constant potential difference of 72 kV. Okay, two plates 3 cm apart and are situated air dielectric medium are connected to a source of, how much is the voltage? 72 kV. Find the electric field intensity between the plates. So he wants his electric field intensity, which is given by E is equal to V by T. You can easily calculate, right? Is it within the permissible value? Right. If a mica sheet of epsilon r is equal to 4 of thickness 1 centimeter, which means in this 3 centimeter case number 2, what he is doing, total is 3 centimeter. What he is doing, mica sheet of thickness 1 centimeter is introduced between the plates, which means only up to 1 centimeter he is introducing mica, which means mica is 1 centimeter, the rest is 2 centimeter is air. Determine the field intensities in air and mica. Given the dielectric strength of air and mica is 30 and 1000 kilovolts per centimeter, and comment on their result. Now we will see how to solve. See the first case up to here, this is first case. See what he has given now. See, assuming only air is available between the plates, what he has given, the field intensity between the plates is given by E is equal to V by T. What is the voltage here? 72 kV, and initially it was 3 centimeters apart. 72 by 3, it is 24 kV per centimeter. And it has already been mentioned that dielectric strength of air is 30 kV per centimeter. But my electric field is 24 kV per centimeter. See, what is dielectric strength? Dielectric strength is nothing but the maximum voltage which it can withstand, the maximum field which it can withstand. After that, it will experience a breakdown. So, normal, what is the maximum strength given? It is 30 kV per centimeter. If you apply more than this one, it will experience breakdown. But right now, what is my electric field? V by T, it is 24 kV per centimeter, very less than this one. So, my material will be very safe and it will not experience any breakdown. See, the above value is safe and the dielectric will not experience breakdown. Now, if I introduce mica now, which means there is one, now this is the case, 1 mm mica is there, 2 mm air is there. Now, if you carefully see, you can do this in two different ways, but let us do it in a simple fashion now. You know that applying, this is a dielectric interface, right? This is a dielectric interface. So what you can do at the dielectric interface, you know the two simple forms. See, the field is in this fashion only. E is always normal here in this case. En is available. Et is not available. Okay, because you are applying voltage here, right? So only En is available, Et is not available. So my E is nothing but En only, or my D is nothing but Dn only. See, you know the boundary conditions here at this point. At this boundary condition, the very first condition is Dn1 is equal to Dn2. If I convert it into E, you know, D is nothing but epsilon naught, epsilon r into E. So this is my expression, which we have already done in the previous lectures. Now I will substitute here. See, epsilon r1 is nothing but my air, it is 1. Epsilon r2 is my copper, it is nothing but 4, which has been given for it. So, see, if I substitute, this is my formula. And for this medium, right, this was the field, right? What is the total voltage now? This is my total voltage, right? V is equal to E into D. This is a normal formula which we infer. But here in this case, there are two fields. This is one field, this is another field. So what I will do is nothing but I will apply E1 D1 plus E2 D2. Right? And my E is exclusively normal field only, because I don't have any tangential field here. So I am reducing this formula to this one. Okay. So now if I substitute this one, yeah. See now, as seen in the figure, what you will be getting? E varies in the direction of normal to plates and is to be computed between two plates over entire 3 centimeter thickness, right? Since this is air, this is mica. Since the lengths are uniform in straight line, we shall divide into two parts. Across air, E1 over thickness 2 centimeters. Across mica, it is 1 centimeter. So this is my formula. E1 we already have. E1 is equal to 4E2. We already had this equation earlier, right? So if I substitute it now, what I will get? 4E2 into 2 in plus E2 into 1. So what is E2? E2 is 8 kV per centimeter. E1 is 32 kV per centimeter. Isn't it? Which means this is of air. This is of mica. But literally speaking, see, which means that the medium now, in this mica, the fields are different. In air, the field is 32 kV per centimeter. In mica, it is only 8 kV per centimeter. But you know that Air cannot withstand anything greater than 30 kV per centimeter. So, but your field now is 32 kV per centimeter. So, what will happen immediately? The air will experience breakdown. So, immediately air ceases to be insulated. So, immediately there will be a breakdown here. So, your voltage now, which is across this one, now the air will experience breakdown. Mica will not experience breakdown because mica strength is 1000 kV per centimeter. Your voltage, your field is now 8 kV per centimeter. Now, in this thing, what will happen now? Air is experiencing breakdown. So, it will not be counted as dielectric medium now because it has experienced a breakdown. So, this dielectric medium is not counted. Only this one is available. But your voltage, what is the voltage which you are having? 72 kV, right? Now, what is the medium now which you do have? I do have only one medium, that is mica, because air already has experienced breakdown. So, medium is now only mica. And what is its thickness? 1 centimeter. So, now what is the strength now? 72 kV per 1 centimeter. So, it is 72 kV per centimeter. Because air has already experienced breakdown. Only mica of 1 centimeter is present now. So, now what will happen? In this case, E2 is 72 kV per centimeter. This is much lower than the rated value of 1000 kV. So, even though it is of only 1 centimeter, it can withstand. And hence, mica sustains without breakdown. So, what is your comment now? Air will not withstand this voltage. So, automatically it will experience breakdown. So, this combination is not suitable. Okay, that is your comment. Now, we will move on to next problem. See, the next problem states radii of two spheres differ by 4 centimeters, and the capacity of the spherical condenser is this one. If the outer sphere is earthed, calculate the radii assuming air is directed. See, radii of two spheres, which means there is a spherical capacitor. I'll take this one as A, I'll take this one as B. What they are saying? B minus A is 4 centimeter. And the capacity of total capacitance is 53.33 picofarad. It is 10 to the power of minus 12 farad. Outer sphere is earthed. What they want? Radii assuming air as directed. So the medium is air with epsilon r is equal to 1. Right. So for this, for what you are supposed to find out? Radii A and B you are supposed to find out. You know, for a spherical capacitor, we have already done this for expressions. For a spherical capacitor, this is the formula, right? C is equal to this one. And this one C is already given here. Epsilon value, you know, epsilon is equal to epsilon naught into epsilon r. Here epsilon r, it is air, so it is 1. So you will get 8.85 to 10 to the power of minus 12. Given separation between the two spheres, B minus A is 4 centimeters, which is nothing but 0.04 meters. So this is the substituting, this is the formula. This is C, right? C value, epsilon naught value, pi value, this is 4, epsilon r is equal to 1, and this is AB, and B minus A is 0.04. If I substitute, what I'll get? I'll get AB is equal to this one. Once I get AB, you know, this is the expression, right? We know A plus B is equal to A minus B whole square plus 4AB square. I will apply this formula. So what I will get if I substitute A minus B, this is 4 square, sorry, 0.04 square, plus I have already obtained here 4 into 0.019. So I will get A plus B. How much it is? 0.28. Now I do have B plus A or A plus B is equal to 0.28. B minus A is equal to 0.04. If I subtract, add, I will get 2B is equal to 0.32. So B is equal to 0.16 meter. So automatically A is equal to 0.12 meters. So this is the way how to determine the radii. Okay. So now my spherical capacitor inner radius is 12 centimeter, outer radius is 16 centimeter. Okay. Now, the last problem for today. Okay. See, this is a parallel plate capacitor A which is charged to 40 microcoulomb at 100 volts. It is then connected 40 microcoulomb to a similar type of capacitor B of 4 times the plate surface area. Find the charge on each capacitor. Which means that initially there is a capacitor with the charge of 40 microcoulombs. The charge is 40 microcoulombs and it is connected across 100 volts. It is then connected to a similar type of capacitor B. This is A capacitor. Okay. Connected to B of 4 times the plate surface area. Assuming that both are connected in parallel. The voltage is now same at 100 volts. So for both the capacitors it is 100 volts. But this charge of 40 microcoulombs, which was earlier on A capacitor, will be now shared by these two capacitors. So what is the charge on each capacitor? Which means he is asking on what basis the charge will be divided. So we will see. Now, assuming two capacitors are connected in parallel, the potential drop across the two capacitors is same at 100 volts. So VA is equal to VB is equal to 100. And both the capacitors share the same charge now, which is nothing but 40 microcoulombs. Now if you see, first of all let's calculate the capacitance. What he said, the second capacitor B was with 4 times the plate surface area. You know, capacitance will be just like epsilon A by D, right? So which means C is directly proportional to A. So if you have more surface area, you will be having more capacitance. B is having 4 times more surface area. So automatically its capacitance CB will be 4 times that of CA, isn't it? So using this particular value now both the capacitors both are connected in parallel, right? When you know that both are connected in parallel, see the combined charge QA is equal to, earlier it was only on charge A, 40 microcoulombs. Now it is to be divided onto two capacitors. So two charges combined charge is now 40 microcoulombs. QA is CA VA, it is CB VB. So now this is the case. You know what is the value of CB? It is 4 times of CA. So VA VB, what is this? 100 because the voltage across these two capacitors is same. So you will get capacitance across A, CA and capacitance across B. Once you know the capacitances of these two, then automatically what you can calculate? You can calculate the charges on these two. QA is equal to CA into VA. QA is equal to CA into VA and QB is equal to CV into VB. You have calculated now 0.08, 0.32 and this is the voltage already. This represents a micro, okay? So 8 microcoulomb, 32 microcoulomb. So now your entire 40 microcoulomb, which was earlier on capacitor A, is now divided into 8 microcoulomb to A and 32 microcoulomb to B. Okay? So this is a way how we will be doing the problems. I hope now you are able to compute the capacitance of different configurations. We will discuss in the next class about other problems on capacitors, and this is your homework. Try to solve this problem, and if possible we will try to solve this in tutorial class. Thank you.